My name's Ananya, and we're from St. John School. And here we have, I guess you guys can introduce yourselves.
I'm Ben.
I'm Caden.
Oliver.
Addison.
I'm a
Great.
senior. Oh, sorry.
No, go ahead.
I'm a senior, and we're all seniors except for Ben. He's a junior.
Okay. So whenever you're ready, you can feel free to get started.
Okay, perfect. Hey everyone, my name's Ananya. My teammates Caden, Ben, Oliver, Addison, and I made up entry number 16573 of this year's Math Modeling Challenge, where this year we were tasked with modeling e-bike growth through making 3 models. First, we were asked to model the growth of the e-bike industry by predicting how many e-bikes would be sold in the next 3 and 5 years in both the UK and the US. Next, we were asked to look at why e-bikes are growing in the first place by weighing various causal factors that had influenced and caused e-bike proliferation to ultimately attempt to determine which variables have been the most influential in causing e-bike growth. And finally, we looked at why this is important and why we should care by quantifying the impacts of e-bikes to ultimately project the impact of e-bikes on both average lifespan and carbon emissions in the UK and the US, so that ultimately we could not only understand how much e-bikes are growing and why they're growing, but what this means on the world around us. So with that, let's get to our first model. Part 1, the road ahead. The first step in predicting how much e-bikes would grow was obviously collecting data, which we did by collecting data on how many e-bikes were sold in the UK and the US every year, starting back in 2012 and all the way up till now, in 2022. We employed a wide variety of published studies to compile the data table that you see right here. Before we made our model, we also had to make a couple key assumptions. The first and most important being that e-bikes grow logistically. This makes sense empirically because other popular technologies, say the iPhone, have been shown to grow logistically. Also, logistic growth implies a carrying capacity, or a maximum value reached. And this also makes sense for e-bikes, because we think that past a certain point, people aren't going to want to buy e-bikes anymore, implying that there is a maximum number of e-bikes that will be sold, or a carrying capacity. Other important assumptions we made were that e-bikes are going to have a constant lifespan and stop working after a certain time because they're reliant on lithium-ion batteries, which also have a constant lifespan and eventually stop working. And finally, we assume that people only buy a new e-bike when that e-bike stops working, instead of when there's like some new trend in the market, which was an assumption we just had to make for the sake of tractability. With that, let's get to the nitty-gritty of our model, the logistic equation, which was the basis of this model. We use a pretty standard logistic equation, which you can see right here, with variables being year, inflection point, growth rate, and carrying capacity. The only interesting assumption we made was setting our carrying capacity equivalent to the population size in the 2 nations we were attempting to model. This assumption makes sense because we're saying that every citizen is capable of owning an e-bike, so the maximum number of e-bikes is going to be in a world where everyone has one. Obviously, some people might not want e-bikes, but some people might buy multiple, so the equivalence still makes sense. We also had to make this assumption for the sake of tractability, because attempting to change the carrying capacity by saying that a certain percentage of people would want e-bikes was impossible, so we had to do this in order to complete our model. Before we get to results, let's evaluate how well this worked. We jittered all our data up and down 2% to recalculate our growth rate and then recalculate our results to see if there was any substantial change. And fortunately, there wasn't. That corroborated our model and indicated the strengths I'm about to explain. Our first strength is broadness. By looking at e-bike growth alone, we can assess a wide variety of other economic trends in the market. Second, thrift. We only needed a dozen data points per country for this model to work. And finally, expandability. We can keep using this model in the years to come by just adding new updated data. That's not to say that this model was perfect. It just generalized e-bike growth and assumed that it's going to keep following the same trend, when in reality, things might change in the market. And it also has little specificity because we're only looking at overall e-bike growth, so we don't know how specific variables are going to change it. But fortunately, we do get to specific variables later on in part 2. And with that, let's get to our results. In 3 years in the UK, we expect to see 322,000 e-bikes sold, and in the US, 1907,000 e-bikes sold. In 5 years in the UK, we expect to see 563,000 e-bikes sold, and in the US, 396,000 e-bikes sold. And that's part 1.
Moving on to part 2, in this section we are tasked with identifying the most significant variables contributing to the previously predicted e-bike growth. In this section we had 2 models, first a correlation matrix and secondly a multivariate linear regression. The results from this section are going to be important for policymakers to create effective legislation in order to continue to boost the growth of e-bikes. For our models, we needed a few key assumptions, all enumerated here. The most important of which is that correlated factors are accurate proxies for the factor of interest. For instance, we assume that health awareness is accurately proxied by gym memberships, and that the popularity of e-bikes can be accurately proxied by Google Trends, data on the searches of e-bikes. This is necessary for us to evaluate data on less concrete and more nebulous factors like trendiness, environmental consciousness, and health awareness to create a more robust model. The remaining assumptions are necessary for a more robust and accurate linear regression. Now, moving on to our specific model, we had a few key factors we identified from browsing the literature on e-bikes that could contribute to significant changes in e-bike sales. We have GDP per capita, consumer spending, gas prices, lithium price, health and fitness, median age, trendiness, and environmental consciousness. We then established a theoretical framework as to why each of these factors could potentially contribute to a significant increase or decrease in the sales of e-bikes. For instance, trendiness could potentially contribute to an increase in e-bike sales as people are more likely to buy an e-bike when something is more popular. We then collected data over the past decade from both the US and UK on all of these independent variables, interpolated missing data values, and then standardized all data. Then we calculated the pairwise correlation coefficients or correlation values between all of these independent variables in e-bike sales. Although correlation doesn't imply causation, we do know that low correlation drastically decreases the probability that that independent variable has a causal effect on the growth of e-bikes. Then, by isolating for the most probable factors that significantly contribute to the growth of e-bikes, we then created a multivariate linear regression in order to compare the relative significance of each of these factors.
Great. Thanks, Ben. So on this slide to the right, we're going to talk about the correlation that Ben just mentioned. Both of these heat maps reflect the individual correlation values between each independent variable that we use in our model. As you can see, this darker column indicates lower correlation values, which means that each of the independent variables in this column have pretty low correlation, not too much of a similar strengths together. Whereas these bottom rows indicate pretty much a lighter value, which means that they have a stronger correlation. Each independent variable we used in our model has a pretty strong relationship to US bike sales. But in order to investigate the strength of that correlation, we have to put all these variables into the real world, plugging them into our multivariable linear regression and estimating their correlation or their multivariate regression coefficients. Our bar graph to the right is a standardized absolute value of each of these coefficients. We can see that some of the observations we made in the previous slide still hold up. For example, in the US or in the UK, GDP per capita is a pretty weak predictor or strength that is a pretty weak predictor of bike sales at the end of the day. Whereas some of the higher related ones, such as GDP per capita in the United States and in the UK, trendiness are really great indicators of bike sales in the future. Critically, even after jittering all of our data between -5 and 5%, a lot of our values remained relatively constant, boosting our confidence in the model's precision. So now let's take a look at the strengths and weaknesses of our model. Starting with the first strength, compared to something like a random forest regressor where a lot of the relationships are made in a black box, our multivariable linear regression takes real-world assumptions. All of our assumptions are built on real-world analyses, and these allow us to build a strong theoretical framework that makes sense and is intuitive at the end of the day to anybody who looks at the model. But then second strength is predictive power. We can use less data than something like a neural network, which is also not very transparent, and produce these same strong results. I mean, there are of course a couple of weaknesses. First, we'd say linearity. Some of the independent variables do not reflect linear trends. For example, like lithium values oscillate from year to year, and there's not too much of a strong linear trend there. Another weakness that we observed was causality. Our model isolates correlation strength, but this is just one of the this is just one of the downsides when working with big data rather than some sort of like causal study. And then finally, we don't really have collinearity, which means that each of the independent variables are a little correlated. For example, lithium data might be related a little bit to GDP, which means that this could dilute the strength of our model. But passing it on to Oliver for part 3.
Awesome. Okay. In part 3, we were asked to analyze the real-world impacts of our model, specifically on the health and climate of the United States and the United Kingdom. To do that, we need to understand how people are going to be using their e-bikes, I'm sorry. Are going to be using their e-bikes. In their literature, we found 4 main use cases of e-bikes: the commute, the recreational trip, the local trip, and the other trip. We determined average distance values based off of empirical data for conventional bikes and assigned them to each of these trips. We then made the key simplifying assumption that each user would only use their bike for one of these use cases. While this may not be true in the real world, we think people who mainly use their bikes for commutes but occasionally use them recreationally, and people who mainly use their bikes recreationally but occasionally commute with them will often cancel out, therefore allowing us to make this large simplification to the model and make our problem significantly more tractable. The model itself is a Monte Carlo simulation. We start by generating a population of bike users in the target country based off of the bike sales from part 1. We then divide the population based off of the age group, since age is a significant factor in determining how people are going to use their bikes. Finally, we simulate each person choosing a e-bike or choosing a use case for their e-bike based off of sample survey data that we found online. This allows us to determine how far people are going to be using their e-bikes on a daily basis and in terms of the lifespan of an e-bike. Then, using known statistics, we can also determine the form or mode of transportation that these people would have taken without the e-bike. For example, would they have ridden a car, taken public transportation, walked or biked, or not have made that trip at all? Which allows us to do the calculation of the